Imagine a glass of ice water on a hot summer day. At first, the ice is solid, the water is cold. You take a sip, savoring the refreshing chill. But as you leave the glass unattended, the ice begins to melt. The once frigid water slowly warms. Eventually, the ice disappears entirely. This simple process mirrors the universe's fate. Heat flows from hot to cold, seeking equilibrium. The universe, like the glass, will reach maximum entropy, a state where energy is evenly distributed. Stars will exhaust their fuel, galaxies drift apart. The universe will become a cold, dark uniformity, a cosmic graveyard where nothing much happens. It's a chilling thought. The universe has an expiration date. But does this theory hold deeper implications for our existence? To answer, we must delve into the history of thermodynamics. We will explore the evidence and questions it raises about the universe's fate. Join us on this journey through the cosmos. The story of the heat-death theory is a tale of scientific inquiry, of brilliant minds piecing together the puzzle of the universe's ultimate fate. It's a story that begins in the 19th century, a time of great scientific upheaval, with the birth of thermodynamics, the study of how energy behaves. Scientists like Sadi Carnot, James Clerk Maxwell, and Rudolf Clausius were laying the groundwork for understanding heat, energy, and the concept of entropy. Their work provided the foundation for modern physics. In the mid-1800s, Lord Kelvin proposed that the universe, like a winding-down clock, is steadily losing usable energy. As the universe expands and cools, energy becomes more evenly distributed, leading to thermodynamic equilibrium, the heat death. Kelvin's ideas sent shockwaves through the scientific community. The notion that the universe might have a finite lifespan was a radical concept. It challenged long-held philosophical and religious views about the nature of existence. The heat-death scenario sparked intense debates and fueled further research into the laws governing the cosmos. However, Kelvin's understanding of the universe was incomplete. The true nature of stars, galaxies, and the vastness of the cosmos was still shrouded in mystery. The 20th century brought a revolution in our cosmological understanding with the discovery of the expanding universe and the Big Bang theory. These findings forced physicists to re-evaluate the heat-death theory. Despite advancements, the fundamental principles of thermodynamics remain unchanged. The question is not whether the universe is moving towards equilibrium, but how this process will unfold. To answer this, we must turn to present-day research and the brilliant minds grappling with the universe's ultimate fate. The universe's clock is ticking. As our telescopes peered deeper into the cosmos, the 20th century unveiled a dynamic universe. In 1929, Edwin Hubble discovered the universe is expanding. Distant galaxies are moving away, faster the farther they are. The universe is like a balloon, with galaxies moving apart. This had profound implications for the heat-death theory. Would expansion counteract the tendency towards equilibrium? Matter and energy spread out, making uniform temperature harder. This puzzled physicists, leading to re-evaluation of heat death. The expanding universe raised questions about the cosmos's fate. Will it expand forever, growing colder and darker? Or will gravity cause a fiery big crunch? These scenarios became central to cosmological debates. Quantum mechanics added complexity to the universe's fate. Developed in the early 20th century, it revolutionized our understanding. Particles could exist in multiple states, tunnel through barriers, and be entangled. The introduction of quantum mechanics into the cosmological equation had profound implications for the heat-death theory. One of the key principles of quantum mechanics is the Heisenberg uncertainty principle, which states that certain pairs of physical properties, like the position and momentum of a particle, cannot be known with perfect accuracy simultaneously. This inherent uncertainty at the quantum level has profound consequences for our understanding of the very fabric of spacetime. According to quantum field theory, empty space, the vacuum itself, is not truly empty, but rather teeming with virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum and then quickly annihilating each other. These quantum fluctuations introduce a fundamental randomness and uncertainty into the fabric of space-time, making it impossible to achieve a state of perfect equilibrium, even in a hypothetical universe with no matter or radiation. Furthermore, quantum tunneling, another bizarre quantum phenomenon, throws another wrench into the heat-death scenario. Quantum tunneling allows particles to pass through energy barriers that would be insurmountable according to classical physics. This means that even in a universe approaching heat death, with energy levels incredibly low, there's a non-zero probability that particles could tunnel through energy barriers, creating spontaneous fluctuations and potentially even giving rise to new structures. The implications of these quantum phenomena for the heat-death theory are still being debated and explored by physicists today. Some argue that quantum effects could potentially prevent the universe from ever reaching a true state of thermodynamic equilibrium, while others believe that while these effects might delay the inevitable, they can't ultimately prevent the universe from reaching a state of maximum entropy. As our understanding of the cosmos has evolved, so too have the potential scenarios for the universe's ultimate fate. The heat death, while still a plausible outcome, is no longer the only game in town. Cosmologists now consider a range of possibilities, each with its own set of implications for the future of the universe and everything in it. One alternative to heat death is the Big Rip scenario. In this scenario, the expansion of the universe accelerates at an ever-increasing rate, driven by a mysterious force known as dark energy. As the expansion accelerates, the fabric of space-time itself is stretched, eventually becoming so thin that it rips apart, destroying galaxies, stars, planets, and even atoms themselves. The Big Rip represents a far more violent and sudden end to the universe than the slow fade-out of heat death. Another possibility is the Big Crunch, a scenario where gravity eventually overpowers the expansion of the universe, causing it to contract back in on itself. This contraction would lead to a reversal of the Big Bang, with temperatures and densities skyrocketing as the universe collapses into a singularity. While the Big Crunch might seem like the opposite of heat death, some physicists speculate that it could lead to a cyclical universe where a new Big Bang emerges from the ashes of the old, potentially giving rise to a new universe with its own set of physical laws and possibilities. These are just a few of the many scenarios that cosmologists are currently exploring. The ultimate fate of the universe remains one of the biggest unanswered questions in science, and the heat death, while a compelling theory, is just one piece of this grand cosmic puzzle. No discussion about the fate of the universe would be complete without mentioning black holes, those enigmatic objects that warp space-time to such an extreme that not even light can escape their gravitational grasp. Black holes play a crucial role in the evolution of galaxies and the universe as a whole, and their ultimate fate is intertwined with the grand cosmic narrative. According to Stephen Hawking's groundbreaking work, black holes are not entirely black, but rather emit a faint radiation due to quantum effects near their event horizon, the point of no return. This radiation, known as Hawking radiation, causes black holes to slowly lose mass over time, eventually evaporating entirely. However, the timescale for black hole evaporation is incredibly long, far longer than the current age of the universe. The existence of Hawking radiation has profound implications for the heat-death scenario. If black holes eventually evaporate, they will release their stored energy back into the universe in the form of radiation. This release of energy could potentially counteract the tendency towards equilibrium, providing a source of energy even in the distant future when stars have long since burned out. However, the interplay between black hole evaporation and the heat death is complex and depends on various factors, including the rate of black hole formation, the rate of Hawking radiation, and the overall evolution of the universe. Some physicists speculate that black holes could become the dominant form of matter in the distant future. creating a universe dominated by these enigmatic objects. Others believe that the evaporation of black holes could lead to a resurgence of activity, potentially even giving rise to new universes through a process known as baby universe formation. Just as we thought we were getting a handle on the universe's expansion, a curveball came hurtling toward us from the depths of space dark energy. This mysterious force, accounting for roughly 70% of the universe's total energy density, throws a wrench into our neat predictions of a slowing expansion and a potential big crunch. Instead of slowing down, observations show that the universe's expansion is accelerating, driven by this enigmatic force we barely understand. Imagine a car cruising down a hill, engine off, gradually slowing down due to friction and gravity. Now imagine that instead of slowing down, the car starts accelerating, as if an invisible force is pushing it forward. That's essentially what dark energy is doing to the universe. It's like a cosmic accelerator pedal, pushing galaxies apart at an ever-increasing rate. This relentless expansion fueled by dark energy has significant implications for the heat death scenario. As the universe expands at an accelerated rate, the distances between galaxies will continue to grow, making it even harder for heat and energy to be exchanged. This accelerated expansion could potentially lead to a colder, emptier universe, a state of even greater entropy than previously envisioned. The very nature of dark energy remains one of the biggest mysteries in modern physics. Is it a property of space itself, a cosmological constant that Einstein first proposed and then discarded? Or is it a dynamic field, evolving over time and influencing the universe's expansion in unpredictable ways? Until we unravel the enigma of dark energy, our understanding of the universe's ultimate fate will remain incomplete. The concept of entropy, a measure of disorder or randomness in a system, lies at the heart of the heat-death theory. The second law of thermodynamics states that the entropy of a closed system always increases over time. In simpler terms, things tend to become more disordered, not less. Imagine a perfectly ordered deck of cards. As you shuffle the deck, the cards become more randomly arranged, increasing the entropy of the system. Applied to the universe, the second law suggests that the cosmos is moving towards a state of maximum entropy, a state of uniform temperature and maximum disorder where no useful work can be done. This relentless march towards entropy seems to paint a bleak picture of the universe's future, a descent into chaos and uniformity. However, there's a fascinating twist to the entropy story. The universe we observe today is anything but featureless and uniform. It's a tapestry of intricate structures, from planets and stars to galaxies and galaxy clusters. These complex structures, these pockets of order and complexity, seem to contradict the relentless march towards entropy. How did such order arise from a universe supposedly moving towards disorder? The answer lies in the interplay between gravity and entropy. Gravity, the force that attracts objects with mass, acts as a sculptor, drawing matter together and creating regions of higher density and lower entropy. The universe exists in a delicate balance between expansion, gravity, and entropy, shaping its evolution and future. As we explore the universe, we encounter the limits of our knowledge, with mysteries like dark energy challenging our understanding. Albert Einstein's work on general relativity revolutionized our understanding of gravity and laid the foundation for modern cosmology. Stephen Hawking revealed that black holes emit Hawking radiation, slowly evaporating over time and challenging classical views. The standard model of particle physics leaves profound questions unanswered, like the nature of dark matter and dark energy. Dark matter's gravitational influence shapes the universe's evolution, forming galaxies and influencing cosmic structure. Our existence is a fleeting spark in the vast universe, yet our capacity for wonder and curiosity elevates us. The heat death of the universe could pave the way for new beginnings, with cosmic cycles of death and rebirth. The finite nature of the universe adds urgency to our quest for knowledge, making our pursuit meaningful. Our true legacy lies in the knowledge we acquire and the stories we tell, transcending time and space. Section 1. The Echo of Existence. As we stand on the precipice of the cosmic unknown, gazing into the abyss of deep time, the question of the universe's ultimate fate echoes through the corridors of our minds. Will it end in a whimper, a gradual descent into a cold, dark uniformity, as the heat death theory suggests? Or will it be a more dramatic exit, a cosmic crescendo of collapsing spacetime, or a cataclysmic rip in the fabric of reality? The answers, for now, remain shrouded in the veil of cosmic mystery, a tapestry woven from threads of scientific inquiry, philosophical pondering, and a touch of awe-inspiring wonder. What we do know, with a certainty that transcends the limits of our telescopes and the complexities of our equations, is that the universe, in its grand and indifferent expanse, is a stage upon which the drama of existence unfolds. Our species, a fleeting blip in the cosmic timeline, has emerged from this cosmic drama, imbued with the remarkable capacity to question, to explore, and to marvel at the very fabric of reality. We strive to comprehend the universe's vastness, to unravel its mysteries, and to find our place amidst the celestial tapestry, even as we grapple with the humbling realization that our time on this cosmic stage is finite. The heat death of the universe, if it comes to pass, reminds us that impermanence is woven into the very essence of existence. But it also underscores the profound beauty of our transient existence, the preciousness of life's fleeting moments, and the enduring legacy we leave behind through our pursuit of knowledge, our acts of kindness, and our capacity to marvel at the universe's grandeur. Section 2. A Universe of Wonder. The universe is a place of breathtaking beauty and awe-inspiring power. From subatomic particles to galaxy superclusters, from starbirths to galaxies' dance, the cosmos is a symphony of interconnectedness. We, on a tiny planet, have deciphered its secrets, driven by curiosity and a desire to explore. The universe is a gift, a treasure trove of wonder. Let us embrace the unknown with open minds and adventure. Section 3. Our Enduring Quest. The contemplation of the universe's fate can serve as a powerful call to action, reminding us that our time in this cosmos is precious. The knowledge we acquire, the art we create, and the impact we have on the world, these become our enduring legacy. The quest to understand the universe is a quest to understand ourselves. By exploring the cosmos, we appreciate the interconnectedness of all things. Let us face the cosmic unknown with courage and gratitude. We have the power to make a difference in the world. Our legacy of knowledge and hope will inspire future generations. The universe may be finite, but our potential is boundless. Let us cherish the present moment and strive for a better future. We are part of the grand cosmic drama that is the universe.